All right, everyone. So here we have chapter 15, and this is on thermal properties of matter. Here in this chapter, we are going to continue with thermodynamics branch of physics. So we will see some of the nice applications that relate things like pressure, volume, number of molecules. So basically, we are looking at the sort of like a macroscopic and microscopic world. And when you're really looking at some of the properties, like, what happens to the pressure at the microscopic level, you do have to look at, sort of like at the molecular level. So sort of like, let's say what happens to individual molecule, and then kind of generalize it to the entire thing. So that's kind of what we're going to do. We're going to look at in terms of some kind of system, and we're going to look at the state of the system, where we can measure things like pressure, volume, temperature, number of molecules in the system. And then we're going to be able to see what happens to that system when we change some of those variables. So we're going to look at, sort of like, let's say what happens when we change some of those, equations of state. All right, so here's an example. How does the speed of the molecules in the air above the frying pan compare with that of the ones that in the rest of the kitchen? So we'll be able to see, let's say, what happens when, the molecules are, in a little more hotter environment. Generally, what we're going to see here is that the temperature is actually very closely related to the kinetic energy of the air molecules. And we're going to be able to see sort of like, let's say, what is the relationship of, that temperature has to the, energy of those molecules. All right, so how do the atoms of the gas determine its temperature and pressure? And we'll see how the microscopic properties of the matter determine its macroscopic properties. So that's kind of like the key, even though we will not be able to, in this particular lecture, to finish everything and look at all the microscopic and macroscopic relationships, but we should be able to see at least most of those. All right. So what we have here is what we call Avogadro's number. And the reason we're going to be using Avogadro number, which is, if you have ever taken chemistry, you probably know already or heard of this, this number. This is usually used because when we're talking about, for example, container with some, liquid in it, or container with some gas, that means we're dealing with a really large number of molecules. I mean, astronomically large number of molecules. And one way that we kind of always do in science, right? We can sort of like, let's say, start, taking some really large number and define that to be something else, so that it's easier for us to, let's say, talk about it, or, write on the paper. So for example, you take 1,000 millimeters, right? 1,000 millimeters is just basically 1 meter, right? Because 10 millimeters is 1 centimeters, and so on and so forth. That means larger the number, harder it is for us to kind of like, write it on a piece of paper and things like that. So generally then what we do here is we take a really large number of molecules, and here's the number, 6 times 10 to the 6.022 times 10 to the 23, number of molecules, right? What we do here is we take that number and define that number to be what we call Avogadro's number. So we're going to talk about that. That's because, generally, let's say if you're talking about atoms, right, in some kind of container, you have a really large number of molecules. If you're talking about, let's say, stars in the universe, it's a really large number of, stars. Let's say distance in the universe, it's a really large distance. Distance between molecules, it's a very, very tiny distance. But, tiny in a way that it becomes like, let's say, if you start writing that, right, you're going to have to write many, many, many zeros. So that's why what we do here is we use scientific notation, plus we define some of those really large numbers as something else. So instead of, let's say when we go into millimeters, when millimeters becomes large, we use centimeters. When centimeters become large, we use meters. When meters become large, we use kilometers. And then when, let's say, you're talking about solar system, the kilometers becomes insanely high. We use astronomical unit as a measurement, let's say, of length. And when astronomical units becomes really large, if you consider from one galaxy to another galaxy, then we use light years, and then there's a parsec. So there's, a number of ways that we can kind of more or less, minimize how many zeros we're writing in our equations. In any case, so for example, yes, right, because atoms are tiny, we must scatter a mole of them to see human object size. Now, what is mole? So generally, we're going to see here is the mole here is defined as exactly Avogadro number of molecules. So at the right, you're looking at the mole of what is liquid at 18 grams per mole. So like, let's say this is in terms of molar mass. Nitrogen, a gas at 28 grams per mole, but with molecules much further apart than in the water or the salt. And the table salt, sodium chloride, a solid at 58 grams per mole. What it means here is if you take a liquid, right? 1 mole of, let's say, water, you put it on a scale, it's going to be 18 grams. You take nitrogen, put it on a scale, it's going to be 28 grams for each mole. And 1 mole, as we're going to see here, is exactly Avogadro number, which is 6.022 times 10 to the 23 molecules. All right. So, and same thing with, let's say, sodium chloride and things like that. So let's say 1 mole, right, of a substance contains as many elementary entities, atoms or molecules, as there are atoms in 0.012 kilogram of carbon-12. What it means here is we take something and we use it as a reference. So that means if you take, 0.012 kilograms of carbon-12, which is about 12 grams, right? If you take 12 grams of carbon-12, and that's basically going to be a 1 mole of substance, right? And then we kind of use that as a reference. So 1 mole of substance always going to contain Avogadro number of molecules. And N is always, so the capital N is always represent, so this is number of molecules, always number of atoms or number of molecules. All right, so the capital N is always that. So when we use a subscript A, then we know that this number of molecules that we consider is exactly, 6.0, 22 times 10 to the 23. And this is basically Avogadro number, for 1 mole. That means every 1 mole of any substance is exactly this many molecules. So one thing we can also use here is the molar mass, which we kind of already looked at, right? So the molar mass, M, is the mass of 1 mole. So as you could see, right, in the previous, slide, we talked about, a water, right? So let's say a molar mass for water was 18 grams for each mole of that substance, right? So then we have the nitrogen, right? So the nitrogen, as an element, right, had then 28 grams per mole. So, and so on and so forth. That means every time we're using, this molar mass, that, pretty much represents in terms of how many, how many grams, right, of that substance here is in 1 mole of, let's say in 1 mole, which is basically this many, let's say, this many molecules. All right, so let's look at our equation here. So what is molar mass? How can we calculate, let's say, for some particular, let's say, element? We take, you can see, right, molar mass is equals to the mass of a substance that we're given and multiply that by Avogadro's number. Okay, so if you have a 5 grams of, let's say, 5 grams of water, take that and multiply by, the Avogadro's number, then you can figure out how much molar mass of a substance you have. So that means in a way, what you have here is that you can kind of, rearrange all those, right? So you can find the mass and so on and so forth. So you can say the mass of the substance here is, for example, the molar mass divided by the Avogadro's number and so on and so forth. So when the molecule consists of a single atom, the term atomic mass is often used instead of the molar mass. All right, so let's look at this example over here. So we have how many moles are in 1 kilogram bottle of water. Okay, so one of the things we have here is I have to give you one more equation that we can use. So basically, excuse me. So let's take, in terms of, we're given how many moles are in 1 kilogram bottle of water. So we're given what type of substance we have. It's basically liquid water. we're given how much of it, 1 kilogram, and we want to know basically the number of moles. And also we want to know how many molecules. Remember, number of moles is different from number of molecules. So we take the molar mass of water to be 18 grams per mole. Okay, so remember, so we have this mole, what we call, mole here. We represent the mole with lowercase n. Okay, so the mole here is lowercase n. So capital N is the, remember, number of molecules. All right, and you can relate those two with one another. That means number of moles is always going to be equals to number of molecules in the system divided by the Avogadro number. That means this is one ratio that we can always use to, to calculate number of moles. Okay. So, but also what one thing we have here is, remember in the previous equation, we had molar mass, right? Molar mass was equals to Avogadro number times the mass of the substance. That means one thing I can do here is I can, rearrange this a little bit, right? I can rearrange this a little bit and represent this as Na is equals to the mass of the substance over its molar mass. Okay. So now what I have here is then what we can do is then relate those things together. So we can say number of moles is equal to then total number of molecules over Avogadro number of molecules. It's also equal to then mass of substance over molar mass of the substance. Okay, because when we talk about number of moles, this represents exactly this many particles, right? Represents exactly this many particles, so they are equivalent to one another. Then think like this. So then this equation for the number of moles, so you have two equations, one in terms of this ratio, one in terms of the ratio of the mass and the molar mass. All right, so let's look at the first part of the question. It says how many moles are in 1 kilogram bottle of water. That means we want to find, number of moles where mass is given 1 kilograms. Also, we're given the molar mass, which is 18 grams per mole. Okay. That means what we would do here is we would take then, because we don't know how many molecules there are, right? So I can't use this first ratio. So we're going to have to use the second ratio. That means I'm going to have to take number of moles equals the mass divided by molar mass. Because I have the mass, it's 1 kilogram, and I have the molar mass. So, but one thing I have to do here is convert the molar mass into kilograms so I can actually cancel the units of the mass, right? Kilogram and grams cannot be canceled, right? So I have to do 10 to the 18 times 10 to the negative 3 kilogram per mole. Then the kilogram as a unit can cancel out. And what we end up with, 55.6 moles. All right. So that means 55.6 moles in our 1 gram of bottled water. All right. So let's look at the second part, how many molecules. That means we want to find this, N. And then I can use this particular ratio over here where, molar, the number of moles equals number of molecules per Avogadro number. And you can see, right, number of moles, it says that I have Avogadro number of, this many, right? This number of moles of Avogadro number. So that means what I have here is, let's say basically Avogadro number, remember, is 6.022 times 10 to the 23 molecules per mole. That means every mole has this many molecules. And what I have here is I have 55.6 mole of those. Okay, so then I multiply, moles cancel out, and then we get number of particles. And this is 3.35 times 10 to the 25 molecules. All right. That means we find how many molecules are there in 1 kilogram of water. Okay. All right, so the next what we're going to do here is we're going to develop what we call ideal gas law. And to understand ideal gas law, we have to look at what we call, a state of our system before and after. So for example, what we have here is some kind of container with, some substance, could be a water, could be oil, could be gas, right? But, some kind of substance with, it has a mass and it has a number of particles, right? So what we do here is, you can see that this is being our system. This is being our system. There are a number of things we can measure for our system. For example, we have a container that has a definite shape and size, and my entire substance occupies that shape, let's say, and size. That means, here, right, I can find then the volume of my system, okay? Well, I also can put a thermometer here, right, and find the temperature of my system. Well, I can also put a pressure gauge and measure the pressure. Well, one thing I can do here is, well, I can, either measure the mass or number of molecules or the, number of moles of my substance. So that means you can, do in terms of number of molecules, mass, or number of moles. So in a way, those three things are, related to one another, right? But, I can also represent, information in terms of that. So those are known as equations or the variables of my state. So these are variables of my state. Okay, state variables, we can say. And they are related to one another, right? So all related to one another. And one of the ways we can, see how those things are related, that means, for example, right, I my system here, here's my system, and I say, all right, so what I have here is I have a volume of my system. So you take something and measure the, the volume right now. So let's say this is volume 1. That means at this instant, right? So this is my volume. Here's my pressure, pressure 1. Here's my temperature, temperature 1. Here I have this many number of moles and 1. And what I can do here is then I can change something. For example, see there's a piston. What I can do, I can move the piston, right? I, crank this, shaft, right? Kind of rotate, and then the, volume changes. Piston moves up or down. That means what I have here is then, let's say I move the piston all the way here. Well, then I have volume 2, which is not equals to volume 1. That means I have a different volume, right? Because now what I'm doing here is I'm compressing my system, right? That liquid is now compressed because I push the piston up. So what I want to know here is what is the consequence of this, decrease in volume? Because now volume here is this much instead of what it was before. What happens to the pressure? Is pressure 2 is same as before or different? How about the temperature? Is it same as before or different? How about number of moles? Basically I do something to my system and then I see what happens to other variables, how the other things are related, to the change. That means what I have here is basically this, variables of state, and my state is then can be described in terms of those initial variables, initial pressure, initial volume, initial temperature, number of molecules, and then we do some kind of, experiment. We change 1 or 2 or 3 things and then see what happens. Let's say it's a little bit later time. Let's say we compress and then start measuring things all over again, or we expand and start measuring things all over again, and then we see like what happens when you increase pressure, the volume, what happens to the temperature, what happens to the number of moles. This I have this this simulation that I want to use to demonstrate some of those relationships. So let me do that over here. All right. So here's what we have. Basically, a system. So a system, you can see, right, has a definite volume. That means, basically the shape I can measure in terms of its volume. There's a basic thermometer there that measures things in, it can measure in Kelvin, or it can measure, let's say, in Celsius, right? And there's a pressure gauge that measures in atmosphere or measures kilopascals. And what I have here is I can expand or compress my system, right? And also what I have here is I have a pump that I can, use to, pump some molecules inside. All right. Also what I can do here is there's a hot source, hot reservoir. I can increase the temperature in my system or decrease by basically putting on top of the hot or cold reservoir or like a hot plate or something like that. So let's see what happens. So let's look at the, right now I have nothing there. So what I'm going to do here is I'm going to then pump some, let's do it in terms of Celsius. Let's say I'm going to pump some molecules and let's see what happens to pressure. See, there are no molecules, no pressure. So I'm going to then pump some molecules and look at the pressure. Now I have 35.1 or, let's see. Remember, pressure is then when they start colliding with the wall and all of those things. So basically what I have here is I have some number of molecules and I can calculate them or, so not count them and then see how many moles of those molecules I have. That means if I count them and I have, 6.022 times 10 to the 23, I can say, right, I have 1 mole. If I have double that, I can say I have 2 moles, something like that. But here's important relationship that I wanted you guys to see is this. See, when I increase the number of molecules, right, pressure increased. That means pressure, so pressure then related, right? So let me, black on black doesn't work. So pressure is proportional to number of molecules because number of molecules, increase. See, if I pump more, see the pressure increases. That means more molecules, more pressure. All right, so now let's see what we have. Look at the temperature. Let's say right now I have 27 degrees Celsius. And you could see, right, temperature also increased because of that. But let's say what I'm going to do here is I'm going to increase the temperature in my system. And by doing that, what I'm going to do here is I'm going to basically put this sort of like, let's say, on a hot plate, which transfers heat into my system, and then heat makes those molecules move faster. As they started moving faster, look at what happens to my temperature. It went all the way to 233 degrees Celsius. And look at the pressure. Pressure increased. I don't know if you guys noticed that or not. See, when I increase the temperature, look at the pressure. Temperature increases, pressure increases. See, now temperature decreases. I put it in a cold plate, right? Like an ice bath. So the pressure decreases because temperature increases. That means what we get here is pressure proportional to the temperature. Because I increase temperature, increase pressure. I decrease temperature, I decrease pressure. All right, so what else then I can do? Well, I can also change the volume. Look at the pressure. So I'm going to decrease the volume. I decrease the volume. See, pressure increased. Why? Because molecules collide with the wall more often because there's a smaller distance for them to go to hit the walls. I make the volume bigger, pressure decreases. You can see, right? That means, smaller the volume, bigger the pressure. Bigger the volume, smaller the pressure. That means what we have here is a pressure that is inversely proportional to volume. All right, inversely proportional to volume. That means what we end up here is we end up seeing how the pressure related to those 3 quantities. Okay, and I'm gonna upload this. I'm gonna post this on on Canvas so you guys can play with that. It's pretty cool. So, but the idea here is, let's go back to the slides. Okay. Well. Okay. So what I have here is this. So this kind of like gives us all that. So that means pressure should be proportional to the temperature of the gas, as we noticed. Pressure should be inversely proportional to the volume of the container. Again, we saw that. And then pressure should be proportional to the number of gas particles. We also saw that in the simulation. That means we have how the pressure is proportional to basically number of molecules, temperature, and then inversely proportional to the volume. Okay. So then when we go from proportionality sign to equal sign, we usually introduce some kind of constant. And that constant in one case is what we call this Boltzmann constant, KB. Okay, so that means what we have here is, so the pressure equals N times this Boltzmann constant B times temperature divided by the volume. But usually what we do here is we basically call the pressure, volume, temperature, and amount of substance as those state variables. And then we use then this relationship that we just looked at, right, in terms of how those are related to one another. And we rewrite this in a different way. So again, moving the V to the other side. So this becomes PV equals then N KB times T. Okay. Now, one of the things we're going to see here is then this N times KB also equivalent to number of moles times another constant, which is, known as a gas constant. That means I have two equations of the ideal gas law. One in terms of number of molecules and another one in terms of number of moles. And usually the second one is the more commonly used equation. But then generally then what I have here is R is 8.314 joules per mole Kelvin, or 0.08214 liters times atmosphere mole per Kelvin. That means what I have here is you use this value for the constant R, the gas constant, if your pressure in Pascal and volume in cubic meters. Okay, and then you use this for the R if your pressure is in atmosphere and volume in liters. Because look at what I have on the left side. It's pressure times volume. All right, so what is pressure? Remember, it's technically force per, per area. But what is force per area? It's Newton per meter square. And then there's volume. So then, that means this is pressure times volume, which is meter cube. See, I cancel those and I end up with newtons times meters. If you remember, that's equivalent to joules. That means this is basically nothing but energy, equivalence. So P times V is equals to energy. N times R times T is technically also basically energy. All of them combined together is represents, the energy. All right, in any case. So those are the equations of state. And what I have here is then whenever you are looking at the state at some instant of time, then you can measure pressure, volume, number of moles, temperature, and see what happens to the other variables when you change. At least right now, we understand that when you change the volume, pressure, changes. And when you increase volume, pressure decreases. When you decrease volume, pressure increases. That means you should be able to kind of more or less predict some of those things that we just talked about. All right. So now here's what we also have. So from this, you can determine that 1 mole of any gas at atmospheric pressure and at 0 degrees is 22.4 liters. Okay, so using this, you basically can, demonstrate that. All right, so one interesting thing we can do always is keep one of those variables constant. That means, for example, so you have pressure, volume, temperature, and number of moles. Okay, so let's say 1, 1, 1, 1. This is initial state. And then you go and change something. So this is then, let's say, P2, V2, T2, N2. Now, this particular one tells you that you keep the constant temperature. That means you basically do an experiment where T1 is equal to T2. That means you are, doing an experiment with the gas, but keeping the constant temperature. That means you might change the pressure, change the volume, change the number of moles, while all at the same time, the temperature never changes. Or you can do an experiment where you keep the pressure constant. That means you can then change the volume, change the number, temperature, other things, but pressure never changes. So this is known, that the first one is known as Boyle's law. This one is the Charles law. You can also do when volume of the gas is constant. So this Guy-Lesagg's law. And this one is basically the volume is constant, and then you change the temperature, which changes the pressure, and so on and so forth. That means, sometimes you can actually do an experiment where some things are constant, some things change, or you can do an experiment where everything changes, depending on the type of experiment you have. All right. So one thing we can do here is always do a graph. Remember, we, in physics like to use graphs to demonstrate some of those, relationships. And here also, what we have is we take the pressure, put it in a vertical axis, then the volume in the horizontal axis. So PV diagram. So this is known as a PV diagrams. This diagram is a two-dimensional diagram giving us what happens. So let's say, think like this. If you're here, state 1, and let's say you go down like this, from 1 to 2. What happens here is the pressure, you have P1 and P2, pressure decreases. Well, when the pressure decreases, if you look at volume, well, volume didn't change at all. That means you can have sort of like, let's say, an experiment where you decrease the volume, decrease the pressure, but keep the volume constant, right? Just like we saw that previous, slide, right? So this is when the volume of the gas constant, we call it the Guy-Lassax's law. So, but one of the things we're going to see here is, so let's say then what happens to the other variables? Well, we can also look at the other variables too, but for example, the temperature also can be imprinted into this PV diagrams, but it's not as straightforward. So let's look at, for example, this graph over here. Over here, we have pressure on the vertical axis, volume on the horizontal axis, but we have those blue lines. Well, those blue lines actually represents the temperature. It shows how the temperature changes on this graph. But the lines that you have is unique in a way that we take third dimension and imprint this into the second dimension, or two-dimensional graph. That means, for example, if I take this first line, see the first line goes like this. Okay. All right, so you might think, okay, so what happened, you might think that the temperature changes because that line kind of goes like that. Well, no, the idea here is that that line represents one temperature. The next line, so let's say line 2, represents another temperature. That means along that line, my temperature never changes. For example, if I'm doing an experiment where my initial state is right here, this is my initial state. Then I go from that point and measure, let's say, pressure 1, and then I measure the volume 1, right? So see, pressure and volume is measured for this state 1, and I measure temperature 1, which is this guy over here. Then I do an experiment where I end up right here. So let's say this is my state 2. Well, state 2, I can measure the pressure. Here's pressure 2. And I can measure the volume. Here's V2. What I can see here is my volume increased, my pressure decreased. And that's always the case. Remember, when you increase volume, pressure decreases. But then the third variable that I can also measure, temperature, then I can look at in terms of where I am on those lines. By the way, those are known as isotherms. We're going to see them in a little bit. So where I am on that line compared to before, and I can say, right, I'm still on the same temperature line. That means my temperature 1 and temperature 2 for this particular, like let's say, right? So don't confuse that with this temperature. That means that this is the state number. So temperature of state 1 compared to temperature of state 2, they're the same because I'm still on the same temperature line. Okay, so that's kind of what we have. This is the Boyle's law. That means we do an experiment where the temperature doesn't change. Now, here's another line which gives me another temperature. And here's another line which gives me another temperature. And how are those temperatures compared? Well, technically what I have here, temperature is increasing in that direction. So you can see, right, temperature 1 is the lowest because T2 is greater than T1, T3 greater than T2, T4 greater than T3. That means closer you are to the origin as an isothermal line, lower the temperature. Further you go, higher the temperature. So that's kind of like one of the things we have. That means you always can look at those, three things in the PV diagram: pressure, volume, and temperature. So let's look at, and solve some examples here. All right, so 20-liter tank contains 4.86 times 10 to the negative 4 kilogram of helium at 18 degrees Celsius. Probably period there. The molar mass of helium is 4 grams per mole. Okay. How many moles of helium are in the tank? And what is the pressure in the tank in pascals and in atmosphere? So what we have here is this. So let's say you can, even look at it in some kind of graph. So this is pressure, this is volume, and we're told that you have a 20-liter tank. That means you're given some kind of volume. So let's say somewhere over here. And you're given the mass, right? So here's your container, right? Here's a tank. You have some kind of, a water, right? Not water, so helium. And you also measure temperature. And this is like 18 degrees Celsius. That means you're given the volume in terms of 20 liters. You're given the mass in terms of 4.86 times 10 to the negative 4 kilograms. And you're given temperature, which is 18 degrees Celsius. Also, we are told that it's helium, and helium has a molar mass of 4 grams per mole. Okay. Now, one thing I can do here for part A, right, says how many moles of helium are in the tank. Okay. So one thing I have here is this. So I'm given the total mass of how much helium I have in kilograms, and I'm also given the molar mass of the helium. Again, so we learned that number of moles can be calculated by the total mass in kilograms divided by the molar mass. That means I can do 4.86 times 10 to the negative 4 kilograms divided by the molar mass. But I need to convert that to kilograms, so 10 to the negative 3 kilogram per mole. And then I can cancel the kilograms and find number of moles, which is 0.122 moles. That means I can easily calculate number of moles, right, if I'm given the mass or the molar mass. All right, so that's part A. All right, part B says, what is the pressure in the tank in pascals? Now what I have here is, so I had one state variable, which is the volume, another state variable, which is the temperature, and I have another one, which is number of moles, right? 0.122 moles. And what I want to find here is the pressure. Okay. That means for this particular state, I can then use PV equals nRT then to solve for pressure, which is nRT divided by V, and I have pretty much everything that I want. All right, so N here is 0.122. The gas constant here is 8.3145 joules per mole Kelvin. And here, see the temperature by itself. So I cannot use the 18. I have to convert it to the Kelvin, which is 18 plus 273. And that gives me 291. 291 Kelvin. And then that divided by the volume. Well, volume has to be in, because I'm using this gas constant, it has to be in cubic meters, but I'm given in liters. Then volume, which is then 20 liters, is then, what we do here is 1 liter is 10 to the negative 3 cubic meters. So then we multiply, then we get 20 times 10 to the negative 3 cubic meters. Then come back here, 20 times 10 to the negative 3 cubic meters. So we get pressure as 1.47 times 10 to the 4 Pascal. Now, this is also, we're told to find it in atmosphere. So one thing you do here is you take that number, 1.47 times 10 to the 4 Pascal, and say, okay, so 1.013 times 10 to the 5 Pascal is 1 ATM, and calculate that. All right, so I kind of don't have room for that, but just, you should be able to just do that calculation and find the pressure in atmosphere. Okay, let's look at another example. Here I have a gas is contained in an 8-liter vessel at a temperature of 20 this 8 here technically should be degrees, so 20 degrees Celsius. and the pressure of 9 atm. So determine the number of moles of gas in the vessel and how many molecules are in the vessel. All right, so again, what we're given here, volume, 8 liters. We're given temperature, 20 degrees Celsius, and we're given then pressure, 9 atm. Okay. And what we want to find is basically number of moles for A. So what is N, number of moles? All right, so it should be an easy calculation for us because this equation, PV equals nRT, allows us to calculate N if you have P, if you have V, and if you have the temperature, and R is a constant number. And we do have all of those. So that means we should be able to, do this calculation. All right, so one thing we do here is we have to take the pressure, 9 atm, and convert it to Pascal. Or here's the thing. So in the slides, I have everything converted to Pascal, but I'm going to show you that one thing you can do here is because you have in, let's say liters and atmosphere, so you technically can use that. So 80 liters. And what you do here for R, for the constant, you use then the other, which is 0.08214 liters times atm, atmosphere per mole Kelvin. Because then here, this still has to be converted to the, Kelvin. So becomes 293 Kelvin. But see here, atm cancels with atm, liters cancels with liters. So you don't have to convert that. And you will, calculate exactly the same thing regardless. So this one going to give you 2.99 moles. That means you can use AN, that means atmosphere for pressure as a unit, liters for volume as a unit, but you have to make sure that you're using the second, gas constant, because the second one is in terms of liters in atmosphere. But if you want, you can always use the SI units, right, which is in terms of Pascal, cubic meters, and then use the first one, which is, 8.314 instead of 0.08214, right? So make sure that you guys can understand that part. All right, so this is part A. Part B, what do we want? How many molecules are in the vessel? Well, that's easy because we have this equation where number of molecules is equals to number of moles times the Avogadro number. So 2.99. Remember, because we're saying here is I have 2.99 of the Avogadro number of molecules. That is 2.99 times 1.602, 602 times 10 to the 23 molecules per mole. Remember, this is mole, so the moles cancel out. That means number of molecules that we have here is 1.8 times 10 to the 24. All right, so that's my answer for the part B. All right, here's another one. It says a large cylindrical tank contains 0.75 cubic meters of nitrogen gas at 27 degrees Celsius and 7.5 times 10 to the 3 Pascal, which is absolute pressure. And in the ideal gas law, we always use absolute pressure to calculate things. All right. The tank has a tight-fitting piston that allows the volume to be changed. What will be the pressure if the volume is decreased to 0.48 cubic meters and the temperature is increased to 157 degrees Celsius? All right, so let's see what we get. So now what we have is two states, right? So here's the first one. So the first one, we're given volume 1 to be 0.75 cubic meters. Pressure 1 is 7.5 times 10 to the 3 Pascal. And we're given temperature 1, which is 27 plus 273, right? In terms of, to find it in terms of Kelvin. So this gives me 300 Kelvin. Okay. and let's say some number of molecules, right? So let's say some, N1 here. We're not given, let's say, how many molecules we have or what is number of moles, but some, N1 number of moles. And then here's my state 2. Well, let me do it here so I have more room. Here's my state 2. Now what I'm given here is this. Volume 2 is 0.48 cubic meters. Temperature 2 is 157 plus 273. That means we'll end up with 430 Kelvin. Okay. And what I have here is pressure 2 is unknown. And here's number of N2 number of moles. So here's what we have. At no point we are told that our container will be then open to atmosphere or will be receiving more number of molecules or less. That means we can assume right away that N1 going to be equals to N2. So that means what I have here is, so I have two equations. Equation 1 describing state 1, P1V1 equals N1 R times T1. And then I have equation 2, P2V2 equals N2 times R times T2, which is state 2. And one important thing here, I know that number of molecules before and after are the same. That means, see, if I take equation 1, then divide both sides by the temperature. So what I have here is then P1V1 over T1 equals N1 times R. Then I take the equation 2 and I do the same thing. Divide both sides by temperature 2. And I get P2V2 divided by T2 equals N2 times R. But see, because N1 and N2 are the same, that means this guy is same as N2 times R. There's the same, right? N1 is same as N2. But N2 is also then equals to P2V2 over T2. That means what I can do here, I can say P1V1 over T1, that ratio equals N2 times R, but N2 times R is equivalent to P2V2 over T2. And this is something that you can always assume will be true whenever you are keeping the number of molecules, the number of moles constant during your experiment, okay? So this ratio, right, this equivalent, right, always gonna allow you very quickly to calculate things. How about this? What if you are keeping number of molecules the same, plus let's say number of, or pressure before and after also the same? Well, then what you would do here, go back to this equation and say P1 and P2 are the same. So let's say P1, V1 are the same, and even cancel those. And you have just V1 over T1 equals V2 over T2. That means number of molecules constant, number of pressure constant before and after, and any change in volume changes the pressure, and so on and so forth. All right, well, we don't have this for this particular example. That means pressure before and after, not the same, because we want to calculate that. And we know that volume changes and temperature changes. But then I can use this equation, right, to then solve for P2. Because P2 here is just, rearranging this equation. It will be then T2 over T1 over V2, then times P1. Okay. And, I have everything, right? Just plug in and calculate. So T2 is 430. V1 is 0.75. And then T1 is 300. And V2 is 0.48. Pressure 1 then was 7.5 times 10 to the 3 Pascal. All right, so we do all of this calculation, right? Plug in everything and calculate. And at the end, we're gonna get a pressure 2 to be equals to 1.68 times 10 to the 4 Pascal. All right, so hopefully you were able to follow this. If not, again, remember, you can always rewind back and watch it again. But that's kind of like what happens when you change, some of your state variables. you can always see if some of them are, constant or not. That means this relationship, this equation, right, is always going to be true and always going to allow you to, quickly calculate things when you change in one state, right, how it will then affect the other ones in the second state. All right. Now, we talked about phases, right, in previous chapter. So we know for the ideal gas, we ignore the interaction between molecules. And, one of the things we have here is that those interactions are what makes matter condense into liquid and solid phases under some conditions. So remember, last chapter, we mostly talked about in terms of some liquids, right? But, this chapter, we're now concentrating mostly in terms of gas. And, you can also look at in terms of, phase change, right, for a gas. And they're more or less kind of similar to the liquid. So each phase is stable in only certain ranges of temperature and pressure. And the transition from one phase to another, ordinarily requires phase equilibrium between the two phases. Remember, when you have ice cube at -15, you change the temperature until you reach ice cube at 0 degrees. And then you melt it until you get then water. So this is ice, this is water, but see both of them at 0 degrees Celsius, right? That means for this stage, which is known as a phase stage, right? You have a phase equilibrium. That means you have the same temperature for ice and same temperature for water, right? That means this is known as a phase equilibrium between two phases. All right. So now we can represent these conditions on a graph with axis P and T rather than P and V. So this is known as a phase diagram. Okay. So each point on a diagram represents a pair of values of P and T. And here's a diagram. So instead of doing pressure versus volume, this is another one that we can use, which is the pressure versus temperature. And it tells you, let's say then, under which pressure and temperature, right, your substance will be, here, like, let's say everything here is solid. That means, let's say you can see, right, if this is the temperature for this, at this pressure, it's going to be vapor. But at this temperature, at that pressure, then it's going to be a solid. That means what determines not just temperature, but also the pressure. So, it's everything obviously a little more complicated than, just first it seems. So this is known as a triple point. Triple point is like solid, liquid, and vapor can coexist. And let's say here's then the line separating, a liquid, and this is, let's say, a gas. Okay, so we don't really use this so much in our class, right? Because you need a little bit more in-depth kind of coverage of things, but let's say we don't have time to go over that in this particular semester. But generally, this particular diagram is very useful when you're looking at, let's say, at the higher level physics. So it's these diagrams are useful, and I imagine you guys have probably used this in chemistry too, because it can also be very useful in chemistry. Okay. So here's phase of matter, right? Atmospheric pressure on Earth is higher than the triple point pressure of water. Depending on the temperature, water can exist as a vapor in the atmosphere, as a liquid in the ocean, or as a solid like iceberg shown here. That means what you see here is three different phases of the same thing, right? So that means water can coexist as a gas, solid, and a liquid. All right. So the last thing I'm going to talk about in this chapter here is the kinetic molecular model of ideal gas. That means generally when you talk about the ideal gas, remember you have insane amount of molecules, and those molecules we can assume that more or less behave in a similar way. So if I right now take one of the molecules and try to see at the molecular level, right, at the microscopic level, I look at what's going on to that molecule, then I can generalize it and say that that's basically same thing happening to all the other molecules. Okay. So in this case, you can think of, like, let's say, some simple assumptions we can make. A container contains a very large number of identical molecules. The molecules behave like a point particles that are small compared to the size of the container and the average distance between the molecules. The molecules are in constant motion and undergo perfectly elastic collisions. And the container walls are perfectly rigid and do not move. Because one of the things we can do here is we can then relate some of the macroscopic variables like pressure and temperature to the microscopic things like, a single, molecule moving around and the colliding with the wall. And then you can look at its kinetic energy based on how much, how fast it's moving and all those things. And we will see here that there is a relationship between the microscopic, let's say variables for this particular molecule, right, or atom, and to the macroscopic world. So in a way, what we're going to try to do here is try to see the, a relationship between the temperature of a container with respect to the molecule motion in the container. All right. So let's start with taking just one molecule and assuming that this molecule is moving in a container and it's colliding with the wall. Remember, every time it collides with the wall, it hits it with some kind of force, and there's this area where it, hits the, the wall, it exerts pressure. So during a collision, the molecules exert forces on the walls of the container. That is the origin of the pressure that the gas exerts. Now, what you can see here is just, this is a little bit of, mathematics involved, where you take the, let's say, here's the velocity, you break it down into horizontal and vertical components. And you can see, right, for us, after the collision, the vertical component has the same momentum before and after, because remember, momentum here is mv, but the momentum in the, so let's say py equals m times vy, and then px equals m times vx. So vertical momentum doesn't change because both were, before and after same direction, but horizontal momentum change because, direction changes. That means there's a change in momentum. Remember, there's a change in momentum. Remember, changing momentum is equals to force acting on it during some time interval, right? We talked about. So in a typical collision, a velocity component parallel to the wall, which is vertical component, is unchanged. And the component perpendicular to the wall, which is the horizontal component, undergoes change in, direction, even if it doesn't undergo change in magnitude. And then what we can do here is there's a, little bit of derivation and algebra that you can, look at it in the book if you wish. But the idea here is then we use all of this to relate, this momentum and relate, kinetic energy, because see, this guy is moving with some velocity, then I can calculate kinetic energy, which is 1/2 mv squared. And then I can say, all right, so this is the kinetic energy of one molecule. And then if all of them are more or less identical, that means same mass. If all of them are moving more or less on average, right, same speed, that means I can look at this kinetic energy of this molecule and use that to figure out the relationship of this guy to the temperature. Because one of the things I can do here is, and I can calculate kinetic energy of molecule 1 plus molecule 2 plus molecule 3, and calculate then basically, and divide this by number of molecules, right? And find the average kinetic energy of the system, okay? So then what we have here is this. So the total random kinetic energy of translational motion of all molecules, that means not the average, but let's say kinetic energy of 1 plus kinetic energy 2 plus kinetic energy 3 plus, dot, 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 and there are billions and trillions of molecules. But I calculate the total translational kinetic energy. There is no rotation because they don't have technically size, or we ignore that. So it's all in terms of just a translational or linear motion. And what we do here is we see that, the total energy, right? Total energy is related to the thermal energy, okay? Is related to the thermal energy of the system, okay? So let's say E thermal. E thermal is then basically the total kinetic energy of the system, okay? Now, if then I actually take this total kinetic energy and divide it by the number of molecules, number of molecules, then what I will get here is I get then average kinetic translational energy. And average translational kinetic energy of an ideal gas, you can say it equals to 3/2 times number of moles times gas constant times temperature, which means the temperature of the system related to the average kinetic energy of those molecules. That means temperature is just another way of saying that molecules are in motion. So that's why when molecules are moving faster, temperature increases. When molecules are moving slower, temperature decreases. Because when the molecules are moving slower, they have less kinetic energy. That means the temperature of the system is less than before. So that's why when we get to absolute zero, 0 Kelvin, well, the temperature is zero, right? And by the way, this is in Kelvin. So this temperature is zero only when the average kinetic energy of all the molecules is zero, which is what absolute zero represents. That means even the most energetic molecule doesn't move anymore. Anyway, so those are basically, how those, some of the things like temperature is a microscopic, variable. So it is related to microscopic world where we're looking at individual particles, their kinetic energy, finding the average kinetic energy in the system and relating that to the temperature. Okay, that means this equation can be used to find then the temperature, right? So temperature is just equals to the average kinetic energy of your system. Okay. Now, one thing we have here is, right, this means that average translational kinetic energy per molecule depends only on the temperature, not on the pressure, volume, or kind of molecule. That means I can have a hydrogen, I can have helium, I can have, any type of substance. Its kinetic energy or how fast it will be moving directly related to only temperature. Or you can say the temperature directly related to basically the average translational kinetic energy. Anyways, that means, see on the left side, you have kinetic energy in this equation. That means it's 1/2 m times average velocity or average speed square. On the right side, then you can actually write it in terms of this Boltzmann constant. So you remember the Boltzmann constant. So it's 3/2 k times t. So you can kind of write it in terms of that as well. So because one of the things we have here is, so on the left side is the, average translational kinetic energy of a gas molecule. Okay. And on the right side, you have 3/2 times constant times temperature. Again, it represents basically how the translational kinetic energy related to the, to the energy, to the temperature of the, in the system for the, let's say, for the particular container, let's say. All right, so I have value for this constant KB. Let me write that down. So this KB here, I usually put the B so that this K here is not the spring constant K or any of those things. So this K here is a Boltzmann constant. And it is equals to 1.38 times 10 to the negative 23 joules per Kelvin. Okay, that's the Boltzmann constant. That means in this equation, I can use the Boltzmann constant to basically represent, at that particular K as a constant. So now the last thing I can have here is, so if you come back here, you can see, right, this is average velocity squared. So if I go back here and then have, for example, right, that equation, if I rewrite, so 1/2 m times v square, and this is, remember, average, right? Remember, this was equals to 3/2 kT. See, I can cancel 1/2, 1/2, and divide both sides by m. Now what I have here is v average, v square of the average is equal to then 3 kT over m. And then since this is squared, I take the square root of both sides. So that's what I have. See, square root of 3 kT over m, and this is equals to square root of v square of the average. Now we define that square root of the v square of the average to be the root mean square speed of the gas. So we write this as VRMS. That means this VRMS is the root of the means squared, right? Mean squared, which is basically equals square root of, v square of the average. So that's the root, right? Square root of the mean squared, right? That means most of the time when we talk about, the speed of the particles in this, microscopic world, we usually use the VRMS. That means, you use VRMS value to represent that. So you can say, right, to compute VRMS speed, we square each molecular speed, divide by the number of molecules, and take the square root, which is, we can just basically then, instead of all that, just say VRMS and just calculate RMS value directly by using this 3 kT over m equation, or 3 RT over then the molar mass. Both of them are, equivalent, and we can use this to calculate RMS values. Because most of the time when we're talking about the speed of the molecules in a container, we usually would like to use the RMS values because they're easily to calculate. And, then we can compare RMS speed of the, let's say, hydrogen compared to RMS speed of the helium. And generally, one of the things we can see at the same temperature, which molecule will be moving faster. See, they have the same temperature. The K is the Boltzmann constant. That means which molecule will be moving faster based on their mass. And lighter ones will be moving faster. That's why, for example, our atmosphere has almost no hydrogen or helium, because they are moving very fast compared to nitrogen and oxygen and carbon, right, in our atmosphere. So they all escape the, Earth's gravitational pull and, escaped into space. That means our atmosphere has very little hydrogen or helium. All right, so we are pretty much done with all the, concepts. Now I have like a couple of examples that I'm going to go over. But as you can see, right, in chapter 15, I'm pretty much looking at a couple of things, right? I'm looking at the ideal gas law and, basically the state variables. And I'm going to be pretty much looking at this pressure and molecular kinetic energy and RMS speeds of the molecules. So let's look at this example here. A cylinder contains a mixture of helium and argon gas in equilibrium at 150 degrees Celsius. What is the average kinetic energy for each type of gas molecule? What is the RMS speed then of each type of gas molecule? So what we have here is this. There's a mixture of helium and argon. So the temperature is 150 degrees Celsius. Okay. Now, what we do here is we don't like to keep things in the Celsius. So we calculate the Kelvin, which is take in degrees Celsius and plus 273. Okay. This should give us 423 Kelvin. All right. So part A, asking what is the average kinetic energy of each type of gas molecule? Okay. So I have one equation for average kinetic energy, which is 1/2 times mass of, then average, let's say square of the average, right? But also I know that this guy is equals to 3/2, right? Times Boltzmann constant times T. All right. That means it's 3/2 times Boltzmann constant is 1.38 times 10 to the negative 23 times then the temperature, which is 423 Kelvin, and just calculate average kinetic energy, which is 8.76 times 10 to the negative 21 joules. Okay. That means any type of molecule, right, will have this kinetic energy at this temperature. They all have the same kinetic energy. How fast will they be moving? Well, it depends, because part B says, what is the RMS speed of each type of molecule? Well, I have two types, right? I have, helium and I have argon. And this equation RMS is then equals to, remember, so, I can actually rewrite it in terms of, let's say 2 times kinetic energy divided by the mass. Okay, because remember, let's say 1/2 mass times VRMS square is equals to average kinetic energy. So 2 times that divided by mass, then the square root, and we had that equation for the RMS, right? So that means, I can have this equation for that. Now, what I have here is, so let's say I'm going to get 2 calculations. See, both of them, get same kinetic energy, which is 8.76 times 10 to the negative 21 joules. But the mass is different for argon and helium. Okay. For example, if I look at the mass of the argon, remember, one of the things we had here is, the mass I can calculate by taking the molar mass and divide by Avogadro number. Okay. So that means I can use that to find, for example, helium is 4 grams per mole, if you remember, right? Divided by 6.02 times 10 to the 23. So this is for the, helium. And then I can do the same thing for example, mass of the argon, which will be, again, this is something that, you can have a tables for, 39.9 gram per mole divided by then, Avogadro number, 6.2 times 10 to the 23. That means the idea here is this. If I'm doing for the helium, right? If I'm doing for the helium, then I'm going to end up the mass of the helium, to be 6.64 times 10 to the negative 27 kilogram per molecule. And for the argon, I'm going to get, again, it's 2 times 8.76 times 10 to the negative 21 joules. Then this is divided by, the mass of 6.63 times 10 to the negative 23, right? Sorry, 26 kilogram per molecules. So what we end up seeing is this. They both have the same kinetic energy because the kinetic energy based on the temperature of the system. But each molecule we're going to have a different speed because of their, mass. So helium going to have a 1.62 kilometers per second, where the argon going to have 514 meter per second. In a way, something like this. So this guy here is moving at 1,620 meter per second. The other one is 514 meter per second. That means helium, because it's lighter, moving over 3 times faster compared to the argon. All right, so one other example here. So a flask contains a mixture of neon, krypton, and radon. And we want to calculate the average kinetic energies of the 3 types of atoms. Okay, so for this one, we basically using this average kinetic energy, right? Even though you have neon, krypton, and radon, right? All of them are different, and all of them have different mass and molar mass and things like that, right? But remember, we assume that it's a flask, a macroscopic system that has this container, and they're all under the same temperature. Remember that kinetic energy is equals to 3/2 K times T. That means the kinetic energy of the flask, basic kinetic energy of all of those mixtures, right, depends on only temperature of the flask, nothing else. They individually will be moving at different speeds, but average kinetic energy here is 3/2. So let's say the Boltzmann constant times temperature, whatever it is, right, we're not given that, but that means they all will have same translational average kinetic energy. All right, so that's important to understand. All right, so our last example. So we have a deuterium, which is an isotope of a hydrogen, is the nucleus of a hydrogen isotope and consists of 1 proton and 1 neutron. The plasma of a deuterium is in a nuclear fusion reactor must be heated to about 300 million Kelvin. What is the RMS speed of the deuterium? Is this a significant fraction of the speed of light, which is 3 times 10 to the 8 meter per second? And what would be the temperature of the plasma be if the deuterium at an RMS speed of equals to 0.1 c. All right, so let's look at part A, which is in terms of finding the RMS speed. Remember, VRMS is equals to square root of 3 kT divided by the mass. Okay, so what we have here is the mass is mass of one proton plus mass of one neutron. Okay, so let's say this would be proton has a mass of 1.67 times 10 to the negative 27 kilograms, plus neutron has a mass of 1.675. Well, this is actually 1.673 because they're roughly identical in terms of mass. Neutron is actually slightly heavier, times 10 to the negative 7 kilogram. That means we end up total of 3.35 times 10 to the negative 27 kilograms. Okay, that means we have the total mass. Okay, and that's technically all I needed, right? So that means, then I can say VRMS is equals to square root of 3 times 1.38 times 10 to the negative 23. Then the temperature, 300 million Kelvin. So that means 300 times 10 to the 6 Kelvin, okay? And inside stars, temperature can actually reach that really high temperature, sometimes even, but this is nuclear fusion, right, in a reactor, right? So then this is divided by the total mass, 3.35 times 10 to the negative 27 kilogram. So what we get is this, 1.93 times 10 to the 6 meters per second. So this is then RMS speed. Then the question is, what is this a significant fraction of the speed of light? Well, let's calculate that. So this will be then VRMS over speed of light. And what we'll get here is this, 6.43 times 10 to the negative 3. That means it's basically, if I multiply this by 100, right, which is 10 to the 2, so we still get 0.643. That means it's, less than 1%, right? Less than 1% of a speed of light. So definitely not significant at all. All right, for part B, so it says, what would the temperature of the plasma be if they have then this speed? Well, for this, then what I do is that I go back to this particular equation, right? And basically rearrange it a little bit differently. So basically, if I take this, if I square both sides, then I have, VRMS square and equals to 3 kT over m, and rearrange and so for the temperature, right? So temperature equals to m times VRMS square divided by 3 times k. So again, plug in the mass, plug in the RMS speed as 0.1 times 10 to 3 times 10 to the 8, divided by 3 times the, Boltzmann constant. What we'll get here is 7.3 times 10 to the 10 Kelvin. So that's a really high temperature, right? So this basically, 73 billion Kelvin. So it's a really, really high temperature. All right. That means, remember, in order for them to move faster, you need to increase temperature. So this was only, a fraction of that, right? Only a fraction of that, less than 1%. 0.1 C means you're looking at the 10% of the speed of light. In the temperature, when the temperature is 300 million Kelvin, it was only moving like about 0.6%. To move 10%, you need 73 billion Kelvin as a temperature. All right, guys, so this concludes the chapter 15.